Learning objectives. In this chapter, the user would learn the following in detail. Semi-structured data. Motivation for the semi-structured data model. Semi-structured data representation. Information integration versus semi-structured data. XML and its data model. Semantic tag. Well-formed XML. Document type definitions using a DTD. Attribute list. Modes of information integration. Wrappers in mediator based systems. Capability based optimization in mediators. Online analytical processing. Data cubes. Materialized views. Capability based optimization in mediators. A typical database management system estimates the cost of each query plan and picks what it believes to be the best. When a mediator is given a query to answer, it often has little knowledge of how long its source will take to answer the queries it sends them. Furthermore, many sources are not SQL databases, and often they will answer only a small subset of the kinds of queries that the mediator might like to pose. As a result, optimization of mediator queries cannot rely on cost measures alone to select a query plan. Optimization by a mediator usually follows the simpler strategy known as capability-based optimization. The central issue is not what a query plan costs, but whether the plan can be executed at all. Only among plans found to be executable, feasible, do we try to estimate cost. The problem of limited source capabilities. Today, many useful sources have only web-based interfaces, even if they are behind the scenes an ordinary database. Web sources usually permit querying only through a query form, which does not accept arbitrary SQL queries. Rather, we are invited to enter values for certain attributes and can receive a response that gives values for other attributes. There are a number of other reasons why a source may limit the ways in which queries can be asked. Among them are: Number 1. Many of the earliest data sources did not use a database management system. Surely not a relational database management system that supports SQL queries. These systems were designed to be queried in certain very specific ways only. Number 2. For reasons of security, a source may limit the kinds of queries that it will accept. Amazon's unwillingness to answer the query, "Tell me about all your books," is a rudimentary example. It protects against a trivial exploiting the Amazon database. As another instance, a medical database may answer queries about averages, but won't disclose the details of a particular patient's medical history. Number 3. Indexes on large databases may make certain kinds of queries feasible, while others are too expensive to execute. For instance, if a book's database were relational and one of the attributes were author, then without an index on that attribute, it would be infeasible to answer queries that specified only an author. A notation for describing source capabilities. If data is relational or may be thought of as relational, then we can describe the legal form of queries by domains. These are sequences of codes that represent the requirements for the attributes of the relation in their standard order. The codes we shall use for our domains reflect the most common capabilities of sources. They are: Number 1. /free means that the attribute can be specified or not as we choose. Number 2. bound means that we must specify a value for the attribute, but any value is allowed. Number 3. unspecified means that we are not permitted to specify a value for the attribute. C of S, choice from set S, means that a value must be specified and that value must be one of the values in the finite set S. This option corresponds, for instance, to values that are specified from a pull-down menu in a web interface. Number 5. O of S, optional from set S, means that we either do not specify a value or we specify one of the values in the finite set S. In addition, we place a prime, example / on a code to indicate that the attribute is not part of the output of the query. A capability specification for a source is a set of elements. The intent is that in order to query the source successfully, the query must match one of the elements in its capability specification. Note that if an element has free or optional components, then queries with different sets of attributes specified may match that element. Capability-based query plan selection. Given a query at the mediator, a capability-based query optimizer first considers what queries it can ask at the source to help answer the query. If we imagine those queries asked and answered, then we have bindings for some more attributes, and these bindings may make some more queries at the sources possible. We repeat this process until either number 1, we have asked enough queries at the sources to resolve all the conditions of the mediator query, and therefore we may answer the query. Such a plan is called feasible. Number 2, we can construct no more valid forms of source queries, yet we still cannot answer the mediator query, in which case the mediator must give up. It has been given an impossible query. The simplest form of mediator query for which we need to apply the above strategy is a join of relations, each of which is available with certain elements at one or more sources. If so, then the search strategy is to try to get tuples for each relation to the join by providing enough argument bindings that some source allows a query about the relation to be asked and answered. Adding cost-based optimization. The mediator's query optimizer is not done when the capabilities of the source are examined. Making an intelligent cost-based optimization requires that the mediator know a great deal about the cost of the queries involved. Since the sources are usually independent of the mediator, it is difficult to estimate the cost. For instance, a source may take less time during periods when it is lightly loaded, but when are those periods, long-term observation by the mediator is necessary for the mediator even to guess what the response time might be. Data cubes. The amount of extra storage needed is often tolerable, and as long as the warehoused data does not change, there is no penalty incurred trying to keep all the aggregates up to date. In the data cube, it is normal for there to be some aggregation of the raw data of the fact table before it is entered into the data cube and its further aggregates computed. For instance, in our car's example, the dimension we thought of as a serial number in the star schema might be replaced by the model of the car. Then each point of the data cube becomes a description of a model, a dealer, and a date together with the sum of the sales for that model on that date by the dealer. We shall continue to call the points of the formal data cube a fact table, even though the interpretation of the points may be slightly different from fact tables in a star schema built from a raw data cube. The cube operator. Given a fact table F, we can define an augmented table cube F that adds an additional value denoted star to each dimension. The star has the intuitive meaning any and it represents aggregation along the dimension in which it appears. Figure, the cube operator augments a data cube with a border of aggregations in all combinations of dimensions. Suggest the process of adding a border to the cube in each dimension to represent the star value and the aggregated value that it implies. The cube operator augments a data cube with a border of aggregations in all combinations of dimensions. Notice that if the number of values along each dimension is reasonably large, then the border represents only a small addition to the volume of the cube, that is, the number of tuples in the fact table. In that case, the size of the stored data cube F is not much greater than the size of F itself. A tuple of the table cube F that has star in one or more dimensions will have for each dependent attribute the sum or another aggregate function of the values of that attribute in all the tuples that we can obtain by replacing the stars by real values. In effect, we build into the data the result of aggregating along any set of dimensions. Notice, however, that the cube operator does not support aggregation at intermediate levels of granularity based on values in the dimension tables. For instance, we may either leave data broken down by day or whatever the finest granularity for time is, or we may aggregate time completely, but we cannot, with the cube operator alone, aggregate by weeks, months, or years. The cube operator in SQL. SQL gives us a way to apply the cube operator within queries. If we add the term with cube to a group by class, then we get not only the tuple for each group but also the tuple that represent aggregation along one or more of the dimensions along which we have grouped. These tuples appear in the result with null where we have used star. A variant of the cube operator called rollup produces the additional aggregated tuples only if they aggregate over a tail of the sequence of grouping attributes. We indicate this option by appending with rollup to the group by class. Materialized views. A view describes how a new relation can be constructed from base tables by executing a query on those tables. Until now, we have thought of views only as logical descriptions of relations. However, if a view is used frequently enough, it may even be efficient to materialize it, that is, to maintain its value at all times. As with maintaining indexes, there is a cost involved in maintaining a materialized view since we must recompute parts of the materialized view each time one of the underlying base tables changes. Maintaining a materialized view. In principle, the database management system needs to recompute a materialized view every time one of its base tables changes in any way. For simple views, it is possible to limit the number of times we need to consider changing the materialized view, and it is possible to limit the amount of work we do when we must maintain the view. All the changes to the materialized view are incremental. That is, we never have to reconstruct the whole view from scratch. Rather, insertions, deletions, and updates to a base table can be implemented in a join view, such as movie prod by a small number of queries to the base tables followed by modification statements on the materialized view. Moreover, these modifications do not affect all the tuples of the view, but only those that have at least one attribute with a particular constant. Many common types of materialized view do allow the view to be maintained incrementally. Periodic maintenance of materialized views. When modifications dominate, it is costly to have materialized views or even indexes on the data. What is usually done is to create materialized views but not to try to keep them up to date as the base tables change. Rather, the materialized views are reconstructed periodically, typically each night when other activity in the database is low. The materialized views are only used by analysts and other data might be out of date by as much as 24 hours. Rewriting queries to use materialized views. Since a materialized view is stored in the database, it is possible to rewrite a query to use a materialized view, even if that view was not mentioned in the query as written. Such a rewriting may enable the query to execute much faster because the hard parts of the query, example, joining of relations, may have been carried out already when the materialized view was constructed. However, we must be very careful to check that the query can be rewritten to use a materialized view. Automatic creation of materialized views. An automated materialized view selection advisor needs to generate candidate views. This task can be far more difficult than generating candidate indexes. In the case of indexes, there is only one possible index for each attribute of each relation. We could also consider indexes on small sets of attributes of a relation, but even if we do, generating all the candidate indexes is straightforward. However, with the materialized views, any query could in principle define a view, so there is no limit on what views we need to consider. The process can be limited if we remember that there is no point in creating a materialized view that does not help for at least one query of our expected workload. We can limit ourselves to candidate materialized views that number 1. Have a list of relations in the from class that is a subset of those in the from class of at least one query of the workload. Number 2. Have a where class that is in the and of the conditions that each appear in at least one query. Number 3. Have a list of attributes in the select class that is sufficient to be used in at least one query. To evaluate the benefit of a materialized view, let the query optimizer estimate the running times of the queries both with and without the materialized view. Of course, the optimizer must be designed to take advantage of materialized views. All modern optimizers know how to exploit indexes, but not all can exploit materialized views. An index on a relation is generally smaller than the relation itself, and all the indexes on one relation take roughly the same amount of space. However, materialized views can vary radically in size, and those involving joins, can be very much larger than the relation or relations on which they are built. Thus, we may need to rethink the definition of the benefit of a materialized view. For example, we might want to define the benefit to be the improvement in average running time of the query workload divided by the amount of space the view occupies. Modes of information integration. There are several ways that databases or other distributed information sources can be made to work together. The three most common approaches. Number 1. Federated databases. The sources are independent, but one source can call on others to supply information. Number 2. Warehousing. Copies of data from several sources are stored in a single database called a data warehouse. Possibly, the data stored at the warehouse is first proceded in some way before storage. Example, data may be filtered and relations may be joined and aggregated. The warehouse is updated periodically, perhaps overnight. As the data is copied from the sources, it may need to be transformed in certain ways to make all data conform to the schema at the warehouse. Number 3. Mediation. A mediator is a software component that supports a virtual database which the user may query as if it were materialized, physically constructed like a warehouse. The mediator stores no data of its own. Rather, it translates the user's query into one or more queries to its sources. The mediator then synthesizes the answer to the user's query from the responses of those sources and returns the answer to the user. Federated database systems. Perhaps the simplest architecture for integrating several databases is to implement one-to-one connections between all pairs of databases that need to talk to one another. These connections allow one database systems D/ to query another D2 in terms that DA can understand. The problem with this architecture is that if n databases each need to talk to the n-1 other databases, then we must write n into n-1 pieces of code to support queries between systems. In below figure, there are 4 databases in a federation. Each of the 4 needs 3 components, one to access each of the other 3 databases. Nevertheless, a federated system may be the easiest to build in some circumstances, especially when the communications between databases are limited in nature. A federated collection of 4 databases needs 12 components to translate queries from one to another. Data warehouses. In the data warehouse integration, architecture, data from several sources is extracted and combined into a global schema. The data is then stored at the warehouse, which looks to the user like an ordinary database. The arrangement is suggested by figure. A data warehouse stores integrated information in a separate database. Although there may be many more than the two sources shown. Once the data is in the warehouse, queries may be issued by the user exactly as they would be issued to any database. There are at least three approaches to constructing the data in the warehouse. Number 1. The warehouse is periodically closed to queries and reconstructed from the current data in the sources. This approach is the most common, with the reconstruction occurring once a night or at even longer intervals. Number 2. The warehouse is updated periodically, example each night, based on the changes that have been made to the sources since the last time the warehouse was modified. This approach can involve smaller amounts of data, which is very important if the warehouse needs to be modified in a short period of time, and the warehouse is large. Multi-terabyte warehouses are in common use. The disadvantage is that calculating changes to the warehouse, a process called incremental update, is complex compared with algorithms that simply construct the warehouse from scratch. Example: suppose for simplicity that there are only two dealers in the hardware system and they respectively use the schemas, and we wish to create a warehouse with the schema. That is, the global schema is like that of the first dealer, but we record only the option of having an automatic transmission, and we include an attribute that tells which dealer has the car. The software that extracts data from the two dealers' databases and populates the global schema can be written as SQL queries. The query for the first dealer is simple. Mediators. A mediator supports a virtual view or a collection of views that integrate several sources in much the same way that the materialized relations in a warehouse integrate sources. However, since the mediator doesn't store any data, the mechanics of mediators and warehouses are rather different. A mediator and wrappers translate queries into the terms of the sources and combine the answers. Shows a mediator integrating two sources. As for warehouses, there would typically be more than two sources. To begin, the user or application program issues a query to the mediator. Since the mediator has no data of its own, it must get the relevant data from its sources and use that data to form the answer to the user's query. The mediator sending a query to each of its wrappers, which in turn send queries to their corresponding sources. The mediator may send several queries to a wrapper and may not query all wrappers. The results come back and are combined at the mediator. We do not show an explicit combiner component as we did in the warehouse diagram, because in the case of the mediator, the combining of results from the sources is one of the tasks performed by the mediator. Example: let us consider a scenario similar to that of previous example, but use a mediator. That is, the mediator integrates the same two automobile sources into a view that is a single relation with the schema. Suppose the user asks the mediator about red cars with the query. The mediator in response to this user query. can forward the same query to each of the two wrappers. The way that wrappers can be designed and implemented to handle queries like this one. In more complex scenarios, the mediator would first have to break the query into pieces, each of which is sent to a subset of the wrappers. However, in this case, the translation work can be done by the wrappers alone. The wrapper for dealer 1 translates the query into the terms of the dealer schema. A suitable translation is an answer which is a set of serial number model pairs will be returned to the mediator by the first wrapper. At the same time, the wrapper for dealer 2 translates the same query into the schema of the dealer which is. A suitable translated query for dealer 2 is almost the same. It differs from the query at dealer 1 only in the name of the relation queried and in one attribute. The second wrapper returns to the mediator a set of serial model pairs which the mediator interprets as serial number model pairs. The mediator takes the union of these sets and returns the result to the user. Online analytic processing. An important application of databases is examination of data for patterns or trends. This activity is called OLAP, standing for Online Analytic Processing, and pronounced OLAP, generally involves highly complex queries that use one or more aggregations. These queries are often termed OLAP queries or decision support queries. Decision support queries typically examine very large amounts of data even if the query results are small. In contrast, common database operators such as bank deposits or airline reservations each touch only a tiny portion of the database. The latter type of operation is often referred to as OLTP, Online Transaction Processing Token OLTP. A recent trend in database management systems is to provide specialized support for OLAP queries. For example, systems often support a data cube in some way. OLAP and data warehouses. It is common for OLAP applications to take place in a separate copy of the master database called a data warehouse. Data from many separate databases may be integrated into the warehouse. In a common scenario, the warehouse is only updated overnight. While the analysis work on a frozen copy during the day, the warehouse data thus gets out of data by as much as 24 hours, which limits the timeliness of its answers to OLAP queries. But the delay is tolerable in many decision support applications. There are several reasons why data warehouses play an important role in OLAP applications. First, the warehouse may be necessary to organize and centralize data in a way that supports OLAP queries. The data may initially be scattered across many different databases. But often more important is the fact that OLAP queries, being complex and touching much of the data, take too much time to be executed in a transaction processing system with high throughput requirements. Trying to run a long transaction that needed to touch much of the database serializably with other transactions would stall ordinary OLTP operations more than could be tolerated. For instance, recording new sales as they occur might not be permitted if they were a concurrent OLAP query computing average sales. OLAP applications. A common OLAP application uses a warehouse of sales data. Major store chains will accumulate terabytes of information representing every sale of every item at every store. Queries that aggregate sales into groups and identify significant groups can be of great use to the company in predicting future problems and opportunities. Example: suppose that Hardwork Automobile Co. builds a data warehouse to analyze sales of its cars The schema for the warehouse might be: a typical decision support query might examine sales on or after April 1, 2006 to see how the recent average price per vehicle varies by state. The query touches much of the data of the database as it classifies every recent sales backed by the state of the dealer that sold it. In contrast, a typical OLTP query, such as find the price at which the auto with the serial number 123 was sold, would touch only a single tuple of the data, provided there was an index on serial number. A multi-dimensional view of OLAP data. In typical OLAP applications, there is a central relation or collection of data called the fact table. A fact table represents events or objects of interest. Often, it helps to think of the objects in the fact table as arranged in a multi-dimensional space or cube. Below figure suggests three-dimensional data represented by points within the cube. We have called the dimensions car, dealer, and date to correspond to our earlier example of automobile sales. A data space such as figure will be referred to informally as a data cube or more precisely as a raw data cube when we want to distinguish it from the more complex data cube. The latter, which we shall refer to as a formal data cube when a distinction from the raw data cube is needed, differs from the raw data cube in two ways. Number 1, it includes aggregations of the data in all subsets of dimensions as well as the data itself. Number 2, points in the formal data cube may represent an initial aggregation of points in the raw data cube. For instance, instead of the car dimension representing each individual car, the dimension might be aggregated by model only. There are points of a formal data cube that represent the total sales of all cars of a given model by a given dealer on a given day. The distinctions between the raw data cube and the formal data cube are reflected in the two broad directions that have been taken by specialized systems that support cube structured data for OLAP. Number 1, OLAP or relational OLAP. In this approach, data may be stored in relations with a specialized structure called a star schema. One of these relations is the fact table, which contains the raw or unaggregated data and corresponds to what we called the raw data cube. Other relations give information about the values along each dimension. The query language, index structures, and other capabilities of the system may be tailored to the assumption that data is organized this way. Number 2, MOLAP or multi-dimensional OLAP. Here, a specialized structure, the formal data cube mentioned above, is used to hold the data, including its aggregates. Non-relational operators may be implemented by the system to support OLAP queries on data in the structure. Star schemas. A star schema consists of the schema for the fact table, which links to several other relations called dimension tables. The fact table is at the center of the star, whose points are the dimension tables. A fact table normally has several attributes that represent dimensions and one or more dependent attributes that represent properties of interest for the point as a whole. For instance, dimensions for sales data might include the date of the sale, the place store of the sale, the type of item sold, the method of payment, example, cash or a credit card, and so on. The dependent attributes might be the sales price, the cost of the item, or the tax, for instance, supplementing the fact table or dimension tables, describing the values along each dimension. Typically, each dimension attribute of the fact table is a foreign key, referencing the key of the corresponding dimension table. The attributes of the dimension tables also describe the possible groupings that would make sense in a SQL group by query. The dimension attributes in the fact table reference the keys of the dimension tables. Slicing and dicing. we can think of the points of the raw data cube as partitioned along each dimension at some level of granularity. For example, in the time dimension, we might partition group by in SQL terms according to days, weeks, months, years, or not partition at all. For the cars dimension, we might partition by model, by color, by both model and color, or not partition. For dealers, we can partition by dealer, by city, by state, or not partition. The result is that the cube is divided into smaller cubes that represent groups of points whose statistics are aggregated by a query that performs this partitioning in its group by class. Through the where class, a query also has the option of focusing on particular partitions along one or more dimensions, that is, on a particular slice of the cube, dicing the cube by partitioning along each dimension. Semi-structured data. The semi-structured data model plays a special role in database systems. Number 1, it serves as a model suitable for integration of databases, that is, for describing the data contained two or more databases that contain similar data with different schemas. Number 2, it serves as the underlying model for notations such as XML that are being used to share information on the web. Motivation for the semi-structured data model. The models we have seen so far, E-bar-L, UML, relational ODL, each start with a schema. The schema is a rigid framework into which data is placed. This rigidity provides certain advantages. Especially, the relational model owes much of its success to the existence of efficient implementations. This efficiency comes from the fact that the data in a relational database must fit the schema, and the schema is known to the query processor. For instance, fixing the schema allows the data to be organized with the data structures that support efficient answering of queries. On the other hand, interest in the semi-structured data model is motivated primarily by its flexibility. In particular, semi-structured data is schemaless. More precisely, the data is self-describing. It carries information about what a schema is, and the schema can vary arbitrarily both over time and within a single database. One might naturally wonder whether there is an advantage to create a database without a schema where one could enter data at will and attach to the data whatever schema information you felt was appropriate for the data. Semi-structured data representation. A database of semi-structured data is a collection of nodes. Each node is either a leaf or interior. Leaf nodes have associated data. The type of this data can be any atomic type such as numbers and strings. Interior nodes have one or more arcs out. Each arc has a label which indicates how the node at the head of the arc relates to the node at the tail. One interior node, called the root, has no arcs entering and represents the entire database. Every node must be reachable from the root, although the graph structure is not necessarily a tree. Semi-structured data representing a movie and stars, as shown. Example. Above figure is an example of a semi-structured database about stars and movies. We see a node at the top labeled root. This node is the entry point to the data and may be thought of as representing all the information in the database. The central objects or entities, stars and movies in this case, are represented by nodes that are children of the root. We also see many leaf nodes. At the far left is a leaf labeled Amitabh Bachchan, and at the far right is a leaf labeled 1975, for instance. There are also
many interior nodes. 3 particular nodes we have labeled AB, DR and SY, standing for Amitabh Bachchan, Dharmendra and Sholay respectively.
These labels are not part of the model and we placed them on these nodes only, so we would have a way of referring to the nodes which otherwise would be nameless in the text.
We may think of the node SY, for instance, as representing the concept Sholay, the title and year of this movie.
Other information are shown, such as its length and its stars, 2 of which are shown. A label L on the arc from node N to node M can play one of 2 rules. Number 1. It may be possible to think N as representing an object or entity, while M represents one of its attributes, then L represents the name of the attribute. Number 2. We may be able to think of N and M as objects or entities and L as the name of a relationship from N to M. Information integration via semi-structured data. The flexibility and self-describing nature of semi-structured data has made it important in 2 applications. As databases have proliferated, it has become a common requirement that data in 2 or more of them be accessible as if they were one database. For instance, companies may merge, each has its own personal database, its own database of sales, inventory, product design, and perhaps many of other matters. If corresponding databases had the same schemas, then combining them would be simple. For instance, we could take the union of the tuples in 2 relations that had the same schema and played the same roles in 2 databases. Independently developed databases are unlikely to share a schema, even if they talk about the same things such as personnel. For instance, one employee database may record spouse name, another not. One may have a way to represent several addresses, phones or emails for an employee. Another database may allow only one of each. One may treat consultants as employees, another not. One database might be relational, another object oriented. To make matters more complex, databases tend over time to be used in so many different applications that it is impossible to turn them off and copy or translate the data into another database, even if we could figure out an efficient way to transform the data from one schema to another. This situation is often referred to as the legacy database problem. Once a database has been in existence for a while, it becomes impossible to disentangle it from the applications that grow up around it. So the database can never be decommissioned. A possible solution to the legacy database problem is suggested in figure. We show 2 legacy databases with an interface. There could be many legacy systems involved. The legacy systems are each unchanged, so they can support their usual applications. For flexibility in integration, the interface supports semi-structured data and the user is allowed to query the interface using a query language that is suitable for such data. The semi-structured data may be constructed by translating the data at the sources using components called wrappers or adapters that are each designed for the purpose of translating one source to semi-structured data. Alternatively, the semi-structured data at the interface may not exist at all. Rather, the user queries the interface as if there were semi-structured data, while the interface answers the query by posing queries to the sources, each referring to the schema found at the source. Wrappers in mediator-based systems. In a data warehouse system, the source extractors consist of: number 1. One or more predefined queries that are executed at the source to produce data for the warehouse. Number 2. Suitable communication mechanisms so the wrapper extractor can subdivision A. Pass ad hoc queries to the source. Subdivision B. Receive responses from the source. And subdivision C. Pass information to the warehouse. The predefined queries to the source could be SQL queries if the source is a SQL database. Queries could also be operations in whatever language was appropriate for a source that was not a database system. Example, the wrapper could fill out an online form at a web page, issue a query to an online bibliography service in that system's own specified language, or use myriad other notations to pose the queries. However, mediator systems require more complex wrappers than do most warehouse systems. The wrapper must be able to accept a variety of queries from the mediator and translate any of them to the terms of the source. Of course, the wrapper must then communicate the result to the mediator, just as a wrapper in a warehouse system communicates with the warehouse. Templates for query patterns. A systematic way to design a wrapper that connects a mediator to a source is to classify the possible queries that the mediator can ask into templates, which are queries with parameters that represent constants. The mediator can provide the constants and the wrapper executes the query with the given constants. An example should illustrate the idea. It uses the notation T implies S to express the idea that the template T is turned by the wrapper into the source query S. Example: suppose we want to build a wrapper for the source of dealer 1, which has the schema cars, serial number, model, color, auto trans, navy, etc. for use by a mediator with schema AutoSmid, serial number, model, color, auto trans, dealer. Consider how the mediator could ask the wrapper for cars for a given color if we denote the code representing that color by the parameter $C. Then we can use the below template, a wrapper template describing queries for cars of a given color. Similarly, the wrapper could have another template that specified only the parameter $M representing a model, yet another template in which it was only specified whether an automatic transmission was wanted, and so on. In this case, there are 8 choices if the queries are allowed to specify any of 3 attributes: model, color, and auto trans. In general, there would be 2 power n templates. If we have the option of specifying n attributes, 2 other templates would be needed to deal with queries that asked for the total number of cars of certain types, or whether there exists a car of a certain type. The number of templates could grow unreasonably large, but some simplifications are possible by adding more sophistication to the wrapper. Wrapper generators. The templates defining a wrapper must be turned into code for the wrapper itself. The software that creates the wrapper is called a wrapper generator. It is similar in spirit to the parser generators, example YACC, that produce components of a compiler from high-level specifications. The process begins when a specification, that is a collection of templates, is given to the wrapper generator. The wrapper generator creates a table that holds the various query patterns contained in the template and the source queries that are associated with each. A driver is used in each wrapper. In general, the driver can be the same for each generated wrapper. The task of the driver is to: number 1, accept a query from the mediator. The communication mechanism may be mediator specific and is given to the driver as a plugin. So the same driver can be used in systems that communicate differently. Number 2, search the table for a template that matches the query. If one is found, then the parameter values from the query are used to instantiate a source query. If there is no matching template, the wrapper responds negatively to the mediator. Number 3. The source query is sent to the source, again using a plugin communication mechanism. The response is collected by the wrapper. Number 4. The response is processed by the wrapper if necessary and then returned to the mediator. A wrapper generator produces table for a driver. The driver and tables constitute the wrapper. Filters. Suppose that a wrapper on a car dealer's database has the template for finding cars by color. However, the mediator is asked to find cars of a particular model and color. Perhaps the wrapper has been designed with a more complex template which handles queries that specify both model and color. Another approach to supporting more queries is to have the wrapper filter the results of queries that it poses to the source. As long as the wrapper has a template that, after proper substitution for the parameters, returns a superset of what the query wants, then it is possible to filter the return tuples at the wrapper and pass only the desired tuples to the mediator, a wrapper template that gets score of a given model and color. Other operations at the wrapper. It is possible to transfer data in other ways at the wrapper as long as we are sure that the source query part of the template returns to the wrapper all the data needed in the transformation. For instance, columns may be projected out of the tuples before transmission to the mediator. It is even possible to take aggregations or joins at the wrapper and transmit the result to the mediator. XML and its data model. XML. XML, Extensible Markup Language, is a tag-based notation designed originally for making documents much like the familiar HTML. Nowadays, data with the XML markup can be represented in many ways. While HTML's tag talk about the presentation of the information contained in documents, for instance, which portion is to be displayed in italics or what the entries of a list are, XML tags are intended to talk about the meanings of pieces of the documents. Semantic tag. Tags in XML are text surrounded by triangular brackets, that is, less than, greater than, as in HTML. Also, as in HTML, tags generally come in matching pairs, with an opening tag like FOO and a matched closing tag that is the same word with a slash like /FOO. Between a matching pair FOO and /FOO, there can be text, including text with nested HTML tags and any number of other nested matching pairs of XML tags. A pair of matching tags and everything that comes between them is called an element. A single tag with no matched closing tag is also permitted in XML. In this form, the tag has a slash before the right bracket, for example, FOO slash. Such a tag cannot have any other elements or text nested within it. Well-formed XML. XML is designed to be used in two somewhat different modes. Number 1. Well-formed XML allows you to invent your own tag. Much like the arc labels in semi-structured data, this mode corresponds quite closely to semi-structured data, in that there is no predefined schema and each document is free to use whatever tags the author of the document wishes. Of course, the nesting rule for tags must be obeyed or the document is not well formed. Number 2. Valid XML involves a DTD or document type definition that specifies the allowable tags and gives a grammar for how they may be nested. This form of XML is intermediate between the strict schema models such as the relational model and the completely schemaless world of semi-structured data DTDs generally allow more flexibility in the data than does a conventional schema. DTDs often allow optional fields or missing fields. For instance, the minimal requirement for well-formed XML is that the document begin with a declaration that it is XML and that it have a root element, that is the entire body of the text. Thus, a well-formed XML document would have an outer structure like the first line indicates that the file is an XML document. The encoding UTF-8 UTF equal to Unicode transformation format is a common choice of encoding for characters in documents because it is compatible with ASCII and uses only 1 byte for the ASCII characters. The attribute standalone equal to S indicates that there is no DTD for this document. That is, it is well-formed XML. Notice that this initial declaration is delineated by special markers less than, question mark, greater than. The root element for this document is labeled some tag.
An XML document about stars and movies program as shown.
Attribute. As in HTML, an XML element can have attributes, name-value pairs, within its opening tag. An attribute is an alternative way to represent a leaf node of semi-structured data. Attributes like tags can represent labeled arcs in a semi-structured data graph. Attributes can also be used to represent the sideways arcs, nesting movies within star.
Program as shown.
Document type definitions. For a computer to process XML documents automatically, it is helpful for there to be something like a schema for the documents. It is useful to know what kinds of elements can appear in a collection of documents and how elements can be nested. The description of the schema is given by a grammar like set of rules called a document type definition or DTD. It is intended that companies or communities wishing to share data will each create a DTD that describes the forms of the data they share, thus establishing a shared view of the semantics of their elements. For instance, there could be a DTD for describing protein structures, a DTD for describing the purchase and sale of auto parts, and so on. Using a DTD. If a document is intended to conform to a certain DTD, we can either subdivision A include the DTD itself as a preamble to the document, or subdivision B in the opening line refer to the DTD which must be stored separately in the file system accessible to the application that is processing the document. Attribute list. A DTD also lets us specify which attributes an element may have and what the types of these attributes are. A declaration of the form says that the named attribute can be an attribute of the named element and that the type of this attribute is the indicated type. Several attributes can be defined in one at least statement, but it is not necessary to do so, and the at least statements can appear in any position in the DTD. The most common type for attributes is CData. This type is essentially character string data with special characters like less than, escaped as in PC data. Notice that CData does not take a pound sign as PC data does. Another option is an enumerator type, which is a list of possible strings surrounded by parentheses and separated by ones. Following the data type, there can be a keyword as required or as implied, which means that the attribute must be present or is optional, respectively. A DTD for stars and movies using IDs and IDREFs. Conclusion. In this chapter, we have covered the following in detail. Semi-structured data, motivation for the semi-structured data model, semi-structured data representation, information integration versus semi-structured data, XML and its data model, semantic tags, well-formed XML, document type definitions using a DTD, attribute list, modes of information integration, wrappers in mediator based systems, capability based optimization in mediators, online analytical processing, data cubes, materialized views.